Let me start the Q&A out by asking, so you'd worked with Claude Poher, you know a fair amount about what he was doing. Now that's something that actually Mark and several of the other people in this conference are familiar with as well. His work is not as well known as Podkletnov's, but it's very interesting, and he claimed to get some results. What are your thoughts on him specifically?
So my impression, so like, for example, again, he's a very bright guy. He's got his master's, and, you know, he's you know, fairly well trained. Poher is in a completely different category. The man is absolutely brilliant. I watched him doing calculations in his head that I couldn't do with a calculator when I was really good at this stuff back in the day. He was just ripping it out. He is a professional. He has a lot of experience with aerospace. He has connections at NASA. Everyone, he's well respected in the space. So he's a serious operator. I went and he showed me his lab. We went and did some things down there. It's a good lab. It's small, you know, but it's in his in Toulouse there, and he's very disciplined in his work, right? So I would say if he does a calculation on it, you know, the only thing, you know, you could argue with him is he's got this pendulum thing that he uses to measure the thrust that it's putting out, and people have criticized and say, oh, maybe that's an electromagnetic artifact or whatever. So you could maybe go after that, but if the measurements from that are correct, his calculations would be dead on the money, in my opinion, right? When he showed me that chart, that would be correct. If he tells me, oh, this is related to Tel Aviv experiments, I would take it quite seriously. I would look at it, which is what I did, right? So that's my general impression of him. And he had some great applications. You know, when I met him, he was looking at microthrusters for satellite applications. Now, from my side, I come from an aerospace background at Northrop Grumman. I know the ramp to get that, to get something into space. Like I talked with the director of the Air Force Research Lab about this. It's like a 7-year minimum ramp to go from I got a new thing to it's going to be flying around in space. And the only way, and that's if you partner up with an existing supplier that knows the supply chain. If you try and do it on your own, he says, you might be dead before it gets into space. I said, okay. And so he knows that space very well. So that was probably a really good application that he was targeting, you know, initially. His wife is a medical doctor, and she had a great application, which I thought was phenomenal. And it worked like this. I think I can talk about it because I think she's not trying to keep it a secret or anything, but basically she took that same gravity wave, or whatever you want to call it, this force beam, and she, being a medical doctor, was looking at it for medical imaging. And I thought, this is fantastic. And I said, how would it work? She said, well, it's a gravity wave. So your body is going to absorb it at different rates. Or the bone would absorb it differently than muscle tissue, than, you know, organs or fat or whatever. And I said, okay, on the back end, we're looking at piezo sensors, right? Yep. And I said, and the idea here would be to get the tiniest piezo sensors you could and get a whole bunch of them, millions, like you would do like for a TV, right? A large screen TV. And so I went out and did some research for her, and I found a Japanese company that indeed makes those piezo sensors, really tiny. You could make an array of them and have, you know, I don't know how many, but good resolution, right? So you could stand someone in front of this screen, if you will, of piezo sensors, and you'd fire this thing, and they'd feel like a gravity push, right? Be like a G-force push. It's non-ionizing. We knew that, right? Claude had done a bunch of measurements on this radiation, you know, so it should be safe. You obviously want to do a lot of safety testing before we tried this, and you get this image. So imagine that you, instead of going in for an MRI and sitting in that machine and the magnets bouncing around, banging around, you could just have a single pulse and get an image, maybe do another one or localize it, the focal length, right? And I thought that was really, really good idea. I don't know if she pursued it, but I thought that was a really, really good application. So those are my impressions of both the Claude Poher and his wife. She's quite brilliant.
Well, thank you. Let me go to Jeremy Reese next. He's got his hand up there. Jeremy, go for it, sir.
Okay, there we go. Now we're unmuted. All right. So a couple things that you mentioned in your thoughts, which were that was awesome, by the way. I wanted to you had mentioned the word ether, which is, like a really old term that's been thrown around, and it's kind of unsure what we were talking about here with regards to the ether. And I think that many of these scientists over the past 10 to 20 years have really defined more specifically what an ether is, or what the ether is. And it's an UNRWA radiation bath. I don't know if anyone else could correct me or kind of elaborate on this, but essentially that there's this microwave background radiation that's just ever present everywhere in the universe. And that there's also an ever present exchange of electromagnetic energy and photonic energy between all parts of the system at any given time. So I think that I think I like that model of the UNRWA radiation, is that it's UNRUH. If you want to look it up, and it's this idea that there's this radiation bath that sort of holds everything together and connects it in a matrix. And that's what gives, rise to space, which space is essentially a structure, which is created by the path of photons through space.
Right.
So, yeah, I wanted to elaborate on that. Then the other thing that you had just mentioned was you had worked with Claude Poher, and you said that there was something else that we had just talked about with regards to Claude. Okay, yeah, I wanted to talk about this idea of in conjunction with some of the ideas that you had about the craft. So the idea is that we could use microwaves to sort of eliminate, you have to kind of move the air out of the way, and air is relatively easy to move out of the way. So is water, if you have the right physics. The South Korea has already posted their videos of their supercavitating torpedo technology, and if it works in water, you're damn right it works in air as well. So there's a number of countries already looking into this supercavitating technology, in conjunction with the other propulsion tech. Because once you can force something and get it going really fast and get it going, you then need to move the air out the way in order to get it going faster. So there's a whole bunch of puzzle pieces beyond just propulsion that are involved in this whole UAP issue that we want to address and talk about. One of the things that it was interesting that came to mind is you talked about these left-handed metamaterials. Metamaterials, specifically left-handed metamaterials, where they have negative permittivity, but some that also can exhibit negative permeability as well, and the very odd optical effects that can occur with those types of materials, where it's essentially like the skin of the craft, if it were a left-handed metamaterial, would essentially, it would turn it completely invisible. It would like almost implode the optical illusion of space-time around that object. And if you could combine that type of technology with, of course, the supercavitating tech, you essentially blast a laser beam straight ahead of you, really, really small, and energize just a short distance, maybe like 20 feet. Well, that's going to be calculated because, of course, if you're going through swamp gas or water, you're probably going to have to, readjust how that works. But it's essentially like a laser that focuses on a point right in front of the craft, or a line of points in front of the craft, and it puts so much energy into that in such a small space that it supercavitates. And that supercavitation effect causes, that bubble, that supercavitating bubble, and you want to time it right so that you fall through the hole created by the supercavitating bubble in front of your craft as you travel. So I think that as long as you have the right physics there, you can do it. I think that in conjunction with these other types of left-handed metamaterial skin coatings, they could potentially do other space-time warping effects where you pump a lot of optical energy into this type of thing. So there's this whole idea of, you know what a Crookes interferometer is, right?
Yes.
So it's weird that photons have momentum. It's proven with the Crookes interferometer that photons have momentum, and that momentum could be a potential source of gravity if we have the right mathematics and understand the interactions, properly, and the dissipation of energy and the exchanges that are taking place. So
it's funny you bring up supercavitation.
Yeah,
because I have some experience with that. So there was a group of scientists that were doing some research, and they asked me to come over to the lab. So I went. They were looking for funding, and we were looking at it as a way, or they were looking at it to use it to split H2O. Cheap way to split H2O. And I looked at the demonstration and whatever, and I understand the principle, what you're talking about. I don't know if that's like, depending on, like, if you look at these nutty craft that fly around, you'd have to have some really high speed switching to, like, if you're going one direction, you decide you're going to make a right, you have to switch that cavitation to this other direction. I don't know how it would react in different media density. Like if you're in water, you have to do a lot of adjustment to it. You'd have to constantly be adjusting this thing, just like you do with a hypersonic, right? If you're going through this atmospheric layers, and you're counting, even pollution is a big deal with the hypersonics, right? So you'd have to do that. My thought was more like, if you have this weird field and it's extruding from on the skin of the craft, would that just in and of itself change the physics of drag? Would it be like a quasi-crystal? Are you familiar with the quasi-crystal concept?
Right. Yeah. So crystals, amorphous amorphous materials are glass, and then quasi-crystals are like the main three structural forms of matter, randomly oriented, crystalline oriented, and then quasi-crystalline.
And then the quasi-crystals, right? So I have a set of pots and pans I bought from France that are supposedly quasi-crystals, right? Which would mean that they would be non-stick 100%. It's a marketing thing. Things stick in there, but it is really slippery. But in theory, another physicist explained, he said, if you can get a perfect quasi-crystal, it would be, frictionless, right? Frictionless material. I said, okay, well, I'm still waiting for those pans to come out. I'll have to do with Teflon and my Citroen pens or whatever for now.
Wow, could you imagine that if it was more durable than Teflon and didn't have like the cancerous byproducts?
This is regular metal, but unfortunately, it's from Citroen, the French company, which is, I have a lot of Citroen cookware, and I was like, well, great, this is going to be non-stick, but with just metal, no Teflon, none of that. But it didn't live up to. Actually, one of them pitted really bad because I left sauce in it, and the acid ate through the coating, and that was the end of that. But the idea would be electromagnetic quasi-crystal type action, right? So like this field that we were talking about, this non-orbital material that's exuding this field outside the skin, would basically might change the physics of when, for example, water, air molecules or whatever come in contact with the skin, instead of like rubbing against it, do they get, I don't know, is there some sort of, maybe Remy could chime in, but would there be some sort of
it's called laminar flow, I think.
Laminar flow, correct. Yep.
And
that's right.
You want to create like that supercavitated bubble around just the surface of the craft so it doesn't actually come into contact with anything, right?
That would work. That's correct.
The idea. If you blast that supercavitating bubble in front of the craft and you're traveling fast enough and you're continuing along the line, blasting that bubble in front of yourself and just falling through the hole that it creates.
That would definitely work. That was a big thing when I was a kid. My dad explained that to me about UFOs, and he said it was basically what you're talking about. That was a big theory back in the 60s, I guess, and 70s. Of how
they're using light. They're using light to push around, so they have a lot of light trapped inside of them, and they can create or generate light through I don't know, whatever energy exchanges they're using. They can create and generate large amounts of light as thrust. And I don't know if there's another effect that goes on at the surface of the craft. You've seen that those videos from UAPtheory.com, where he goes into a couple of very interesting cases of UAP where they have like a mirror lens. It looks like a mirror distortion, like almost like what's called an Einstein ring.
Yeah. Well, Jeremy, if it's okay, I want to jump over. If it's okay, let me jump to Remy for questions and then come back. And I just don't want to take too
cool
long.
Stuff, man. Though I thank you for presenting and
okay. Well, thank you.
Whatever it's worth. I hope it sparks some ideas, mate.
Yeah. So let me go to Remy and then Michael Boyd after that. Remy, go for it, sir.
Yeah. Thanks, Jeremy. That's interesting. And Steve, it's very interesting what Steve says as well. I like this idea that did you see what I put up on the chat there with the frog levitating in the high magnetic field? Maybe it's something like that inside these crafts, like he's saying, like an inertial dampener. You set up this standing wave and it kind of pins you to the craft. And then you get this kind of evanescent wave outside the craft, which, I mean, the accounts that these craft don't generate sonic booms. So I think Steve's onto something there. That's sort of what I wanted to say. And as regards Jeremy, what Jeremy's saying as well, I think that's interesting. That's interesting too. I mean, I think you can, he's talking about laminar flow and so forth. I think if you have air bubbles around whatever, say torpedo, it slips through the medium. You release bubbles around it and it slips through the medium much more easily. And I think shark skin does the same thing. It doesn't have the smooth skin as you think. It has a rough skin. And somehow that allows it to slip through the water. So there may be something to what Jeremy is saying too. That's all I had to say, yeah?
Yeah, appreciate that, Remy. Yeah, I was thinking about it because I was studying the hypersonics and obviously the sonic boom, problem, right? Shockwave collapse and whatever. And yeah, I just wonder if you had a low drag coefficient and you're moving the thing through, are you going to get those shockwave buildups? Are you going to get the sonic boom? I don't know. It's a good question, though.
I have a quick question.
Yeah, go for it, Michael.
Shoot.
Could I trouble you to turn your camera on though, if that's okay?
Okay.
Thank you, sir.
Sure. So, how would you define a non-orbital or semi-orbital material?
Right. So if you go, like I'm speaking from group 3,5 nitrides, right? So you can, for example, go and Google C plane, M plane, P plane, right? In that space, because that's where I'm speaking from. And basically, and I can send a link out if everybody's interested in that sort of thing. And I think it's interesting myself. So, but basically C plane, when you have a crystal structure, you always start with a substrate, right? So we would use either sapphire or silicon carbide, right? So that's your nice structure there. And you would get an orientation from it, right? You would, there's 1-1-1 orientation, it's crystal orientation. And when you're growing crystal on it, for example, you're growing gallium nitride or InGaN, if it's C-plane, it's basically gonna grow sideways. And what that means from a physics standpoint is the electrons in orbit in the material are gonna remain in that layer you've grown when you fire it up and use it as, for example, a LED light or whatever, or a laser or whatever. Let's just stick with the LED light because it's simple. When you fire it up, the electrons are basically self-contained in the material, and at the surface of the material is very little of this. What would we call these pi electrons, or they're orphans that would go out into space above the surface of the material, right? If you grow them semipolar, which is like this, let's say, some of the orbits are going to escape from the material. Not all, but a fair amount, right? Because it's at an angle. It's polarized, correct? It's polarized, non-polarized, polar, non-polar, and semi-polar. In the semiconductor world, that's what I'm speaking from. And then when you go to non-polar, which we call P-plane, that's where the crystals are growing straight up, right? These are hexagonal crystals you're dealing with here. And really tricky, because what they want to do is fall down. It's very unstable, and it grows straight up. Actually, the chief scientist from DARPA, he's like, we're trying to do this in our labs. And he's like, the slightest energy burst, like when you're using, let's say you're using heat or lasers or whatever you're using to center this stuff and make it grow. And then obviously you're going to activate it, right? That's the final step. The slightest increase and all the blades of grass just fall over flat where they want to be. And it's basically, you might as well have saved the time and went with seaplane, which is really cheap to do. And that's what I did and what everybody does. So the idea that I had was, and again, the physics of it are, if it's non-orbital, you get a lot of electrons that are going to escape from the surface of the material. And I guess from a performance standpoint, when you have that unstable or semi-unstable material, that when you, for example, use it to make a light or a laser, you're going to get extreme performance out of it, right? As opposed to the seaplane or even the semi-polar crystals, right? And it stuck in my head as a thing to look at. But if you're interested in the physics of it, just Google GaN, gallium nitride, and then C-plane, M-plane, P-plane, you'll see it come up. And then you'll see some recent articles talking about the non-orbital P-plane stuff and the promise it holds for the future and what you can do with it and so forth.
So also, I guess, is this just for 3.5 semiconductors or all direct bandgap stuff?
Probably for all direct bandgap, but I can't speak to that because my expertise is solidly in 3.5 nitrides. So in that world, like if you Google it, it comes up right away. Like if you just Google P-plane, C-plane, M-plane, it right away comes up nitrides, because that's the name of the game in the nitride space is can you grow this way? Can you grow this way? And then obviously cost effectively and so forth. But it's a great material. I mean, InGaN is great because you can tune it, the frequency of the thing, the band gap, you can tune it just by changing the ratio of indium and gallium, right?
When do you think we'll get to aluminum nitride?
You have it right now.
I mean,
Aluminum
like
nitride stuff is everywhere.
Fidelity as the others.
Yeah, the one that interests me the most, what I talked to the CEO of a company that's building the stuff in Massachusetts is indium phosphide for switching applications. It's really high performance stuff, but obviously very tricky to make, as with everything. What else in that world was interesting? I think just understanding that the less stable the material is, if you can get it to set up and activate it, your performance characteristics go way up. That was the interesting takeaway from all of that.
That makes sense. I mean, I'm curious though why they don't use adsorption chemistry to their advantage. What temperature range is this?
You're talking about you're asking the right questions here. So when I entered the space, the problem was for, let's say for GaN or InGaN, was you're talking about 500-600 C to activate it, to crystallize it and so forth.
That makes
so you
sense.
get problem number one, thermal coefficient of expansion, right? So you have this substrate. Let's say you're an enterprising young man. You say, I'm going to use silicon carbide. So you look at the TC of that, right? Then you have lattice mismatch issues, right? Which you can solve with buffers, right? You can lay down buffers. Aluminum's popular. There's other things you can do to that, but you still can't get away from the thermal coefficient of expansion. So you have your wafer. And let's say you want to go with a nice 100-millimeter wafer, big size, so it's cheap to make. And you lay the GaN or InGaN down on it. You get it to crystallize. It's at 500 or 600 C. And as you're cooling it, the thing starts bowing up, right? I actually talked to the CEO of a company when he was trying this in his thing. And he said, I went over to it with the tweezers and I grabbed the end of it and it just shattered because of the stress it was under. And that's why they were all doing these small wafers, right? For that TCE issue. What I was looking to do in my company, the reason I put all that money and time into it was to drop that to 300 C, if I could. less than 400, 300, like in the range where you could use Kapton polyamide, right? Which is the stuff they used to put on the hard drive. It's a plastic type. You get it from DuPont. It's special stuff. And I was thinking,
if I could
this would be great if we could put it on Kapton and get it to lay up.
If I could add something, also once you get to 300C, now you can start using organic solvents potentially.
Mm-hmm. Yeah.
And then that is what opens up all the adsorption chemistry that allows you to limit the crystal growth in certain directions much more easily.
Right.
And, yeah.
There's all kinds of things that open up at low temp.
I recommend trying borax and erythritol. It's an interesting solvent. It's yeah. Well, I don't know. Actually, that might. No, not for your application. Not with nitrides.
We were using chemical etch for it. For the lithography side.
Hey, drop me. We'll talk about it. Yeah. I mean.
Yeah, I'd love to. The one thing that I wish we would have tried was graphene on the subject. I so wish we would have done that. We might have succeeded. I mean, our main competitor did succeed, and they have the current record for solar efficiency at 43.5%.
Nice.
And we were stuck. The problem was we were stuck with the same problem they were, which is we were trying to make the InGaN graded InGaN, right? So you have different band gaps that respond to different photon colors, let's call it, right, of the sun. And you could tune this material. And, they were transparent. If you did the wider ones at the top and narrow at the bottom, the sunlight would get through and you would get this massive, it has a 70-something% theoretical efficiency of the sun. That's why I targeted it. But the problem was as you start adding indium to it, we had the low temperature thing because we used a different type of physics to set it up. We weren't using heat primarily, we were using something else, right? Something else to basically saturate the atomic structure with energy so that it would crystallize and then activate. You have to activate it obviously with dopants and whatever. But in this case, so the InGaN, so we were playing with it and we kept hitting a wall where if we added too much indium into it, it would phase separate. We were beating ourselves for a couple of years on this problem. It never occurred to me. I mean, I did ask the guys, I said, why do we do a tandem cell, right? Where we go with the indium content, stop, and then do something else. But then you have current mismatches, right? And you have tunnel junction diodes you have to engineer into the material. So in the end, we kind of stuck with that. We didn't have the budget to try for a tandem cell, right?
Multi-junction cells are just harder, yeah.
Correct, right? You know about that. So our competitor did this. They would work in the same material system. I met with them and I met the VC that was backing them out in the Silicon Valley. And what they did, they hit the same wall we hit, the indium wall. So they stopped. They had a nice graded multi-junction, multi-band gap, layer. And they did the second layer. They used a different, I don't know if it was germanium something, right? To pick up the other band gap that were missing from the high indium content. And they engineered the current matching so that, because if they're doing two different currents, one will drain the other. You have to kind of, match the currents from the two levels and you have an insulator between them. And they did it and they hit the record, man. They hit it at 40%, 38% at first, and they got it up to 43.5. And they're using that stuff. I think they were going to use it in these concentrated photovoltaics, right? CPV. We have all these mirrors and it's concentrated and handle like 500 suns, and it's really as good. This stuff will handle high temperature, an InGaN solar cell. It will handle high radiation. I did the math with the Air Force. It'll be good in space for 150 years.
Yeah, if you have a very expensive material, might as well get as much energy on that surface area as possible.
Right, and in space, the other problem with solar is degradation from radiation, right? Radiation hardness. That's the name of the game up there. Its weight is one thing because it's about $10,000 a pound to get it up there. And then the other thing is obviously vibration with the rocket launch. You want to, survive that. And then once you're up in space and you unfurl, it's radiation is your problem. That will degrade your cells.
You just wait till we get the stuff Remy's team is working on in terms of Maxwell's zombies or whatever. Once you have non-ergodic systems like you can get crazy efficiencies without even trying. It's fun stuff.
Yeah, the basic thing that Jack always talks about. Jack Sarfati, have you seen his stuff?
Sure.
All right. So he's always talking about Froelich pumped systems that are far from equilibrium. There's a little bit more to it, but yes. Yeah, you know what I'm saying. That theme of having something that's unstable and pumping it far from equilibrium, you get some interesting effects. And the same thing is true from the semiconductor side. They're far from equilibrium, or they're out of equilibrium, and they exhibit these characteristics that are very interesting.
Yep.
So.
Oh, okay. Well, Michael, thank you. So let me go to, let me go to Michael Boyd, who'd asked a question that, and when it comes to band gaps and hard drives, which Steve, you mentioned both of those, Michael Boyd is like hardcore into both of those. So
great.
He's your guy. Michael?
This is the gentleman I was asking, Michael.
Yeah,
okay.
yeah. Oh,
Yep.
he and band gap. I am, and not to tease you at all, but that is probably the word he's used more than anything else for the last couple of weeks. So
everything's got a band gap, even time. I'm almost out of my band gap. So you were talking about this idea of basically gravitational or space-time metric engineering, basically, is what we're talking using embedded materials. And it sounds like you're pretty knowledgeable about semiconductor physics. So you know this.
Michael, I'm sorry, your mic is fading out for some reason.
Oh, how is this better?
Yeah, better now. Thank you. Sorry.
Okay, I'll get closer to it. So Steve, are you familiar with the term lattice matching?
Of course. It was the bane of my existence. Yeah.
So basically, when you're putting up what's an insulation layer or a passivation, as they call it, semiconductor, right?
Yeah, you're putting a lattice matching layer, right?
You need to have, and one of the ways that they do that is they like gallium arsenide, or what was gallium indium, what was the one?
Yeah. Gallium arsenide is a good buffer. Aluminum you can use, right? That's another good buffer.
Right. So like I worked with mercury cadmium telluride, mercury cadmium telluride. Oops.
Oh yeah, we looked at that. Toxic.
They make infrared detectors.
Right.
And so one of the techniques we would do is we take when we cut the semiconductor tool and then we etch off a layer, get rid of all the damage and stuff, and we got down to the good stuff, I call it. Then we would let it sit for a certain amount of time, and then what was called a native oxide would grow on top of that.
Right.
And then we would grow what we would call glass or some kind of silicon oxide.
Right. That's a whole industry unto itself. That's right.
That would be a type of passivation layer that we would use commonly. And so what we would, and then what I got a patent on is I would take, when I was doing that process, I'd put a bright light on it. And what that would do is it would polarize the dielectric, and that would make it more resistive.
Correct. The light is the key.
What
Frequency light did you use?
This is like back in the.
Oh, so white
80s.
light?
It was just like a
xenon lamp?
An incandescent lamp, like one of those bright 1,000-watt ones or something.
Right. That's what we were using. We were playing with different frequencies, and you got different results based on the frequency.
Certainly. So I did basically. What you're doing there is you're changing the dielectric properties of it.
Correct. That's one thing you're doing. That's one thing. That's a result.
And so, but my point here is, in order for this thing to not build up charge at the interface, you had to lattice match. You had to get, because if you did, then there are these little what we call dangling bonds or traps. It would trap.
Right. That's right. Trap charges.
That created in the silicon oxide, it wasn't a crystal, it was amorphous, it was a glass, right?
Right.
So that meant there was lots of, it wasn't SiO2, it was SiOX.
Right, SiOX.
So you had these, what I call dangling bonds. Well, if you put that in a gamma ray source, it would like disintegrate.
Right.
Disintegrate and still be there. It just would be like
Garbage.
like a short.
Yeah, that's right.
Okay. And so the way we developed to get around that is we came up with another passivation called silicon nitride,
Right. Okay.
Si3N4. And
Yep.
that would, and we could lattice match that to in this case, we're using Indian antimonite, INSB. And it's like a 5.
SB, that's tin, right?
Indium.
Indium is IN. SB would be stibium, right?
Antimony.
Tin.
Indium antimony. Antimony is SB.
Tin, right.
Okay, so in any case, that was the material, and both of them are what's called a zinc blade. You know what I mean by that? It's like a diamond lattice.
Yeah.
Lattice, and that's how we would match it.
Okay.
So now, the reason I'm going through all these details is to try and explain to you how that works with the gravitational.
Okay. Get to that. Let's hear that because I'm interested
So
in
now
that.
you have this whole lattice, these two lattices, you're changing a medium. You're going from a dielectric medium to a semiconductor, right? That's
Right.
There are two different types of matter, or two different types of compositions of matter, okay?
Right.
But by matching the interface, basically that's what makes it so that it works electrically.
Correct.
Same thing happens with gravity at the interface, okay? So, but with gravity, it's not just the electromagnetic part, there's what I call a translational part, or it's like, you think it's still, but if you get down to the protons, they're moving, they're shaking,
Yes.
okay? And the way they shake, and they send out these signals, what I call a song, the electron, okay? So what happens is you got to get the electrons and the protons all shaking and singing and dancing to the same tune. And if you do that, you can create an artificial medium of space-time where it's expanded, like more like Hal Puthoff's. You know Hal Puthoff?
Oh yeah, I've talked to him. Yeah.
Well, he talked about expanded space and denser space time. So when you get closer to a star, right, gravity is stronger. That in when you're closer to the increased gravitational field, time slows. As you get farther away, it speeds up. So time goes faster in space than it does on Earth.
or outside our galaxy, for example.
So think of outside Earth, that's expanded space. Now get rid of all your electrons and think of just the protons are there. And in the, you know how you have intrinsic properties to a semiconductor?
Yes.
So like, so there's an intrinsic density of protons in outer space that's different than it is here on Earth. So think of the like lattice of just the protons are there without any electrons, and they have this little structure to them, but they're farther apart. So you get what I'm saying? So if
I do. I'm
you can
thinking.
spin it. Like the way I found this is by spinning it, using spin, by the motion. Everything's in motion in our universe. There is no at rest. You know when they talk about
Right.
All mass is relative.
Even
So-
absolute motion unto itself.
Yeah.
Right.
So there's nothing sitting still. The Earth's moving around the sun pretty damn fast, and then the sun's moving in the arm of the Milky Way galaxy pretty damn fast, and then the galaxy's moving even faster.
Right.
Well, yeah, and wouldn't that go back to what Mark Sokol's working with the Elzaphan stuff? Because even your atoms are spinning, right?
Yeah.
So
That's the whole point. The atoms, the nucleus of the atom, that's where the gravitational field is carried, because that's where the mass of matter comes from. That's why photons don't have mass. You know, we were talking about that in the chat. You got two beams of photons going past each other the opposite direction. They don't attract each other. That's because they don't have any mass. But matter does, and it's the protons, not the electrons, really. You can freeze out essentially the electrons just by cooling down.
So Michael, let me just see if I get this straight. So you're talking about two different materials, for example, like you were talking about Cyox or whatever, and you're doing something else. So you have two different materials, but they're lattice matched. So everything's working together, which I know very well, right? Because we had to lattice match for our stuff as well. You know, you had your lattice matching, you had your point defects, you had your interstitial defects, and then you had your, what do you call it? Thermal coefficient of expansion, right? Which is the, you know, and these are all the challenges we were dealing with. We did figure out a way to get rid of the defect stuff really well with our process. And we used light to do it.
Yeah,
We were able to push impurities out of the material, which is great, right? Depending on the
depends
material.
on what you're using it for.
Yeah, right. So we had that. We had micro hardness. We also observed from this process, which is very interesting. And the lattice matching thing is obvious. Got to have it. You don't have a functioning device if the lattice mismatch is there, or if you do, it's like unstable. But I never thought to sit down and say, lattice match dissimilar materials, what can you do with them? I was more, well, when I was working on that, I was just trying to get the damn thing to work and get out the door and make money, right? But later I was thinking about, when we were talking about superconductors, is how would you engineer the material like a metamaterial to get the properties you're looking for, right? How does that work? And so but it's kind of over my head every time I read these metamaterial papers. They start talking about ellipses and everything, and I'm kind of lost sometimes with it. It's quite intricate.
Well, the book that I put the link in, you should check that out because it's got some really good information.
Oh, you put a link in there?
What?
You put a link in the chat?
Yeah, I put a link up above in the chat too.
you know, Michael, I didn't see that either. Could you tell me what the name is? Let me look that up. It was metamaterials.
I'll find it. Hold on, give me a second. I'll tell you what.
I maybe you typed that in and it went directly to somebody instead of to everybody.
I'm looking for the timestamp.
I'm looking in the chat. Some really good comments. You know, I'm so busy talking, I don't even read these things. So,
Yeah, well, and I am.
Okay, here it is. It's at 1:11 p.m. I put this link to the book.
Oh, there we go.
Okay, so what I was talking about though is when you're going between one space-time medium to another space-time medium, there's a difference in the inner atomic distance. And what I'm talking about is the protons are like there still, because of virtually being in the crystal, but the crystal lattice dimensions are different. So you have to figure out a way to get between those two dimensions. And that's where this what I call vibrational mode thing comes in. So you get them both vibrate, or they're not really vibrating, it's more of a spin state.
right.
But you get these two mediums into a spin state where they're basically synchronized. And the way I like to think about it is like a capacitor, okay?
Mm-hmm.
And you have like and that's why this book is good, because it has a double negative dielectric, where the permeability and the permeability are both, and if you put them both if you get these two dielectrics next to each other, you can basically make it disappear. Make it like an optical cloaking. Essentially, we were trying to do the same thing, but not optically. We're trying to do it basically with the space-time medium.
I got you.
And so, and then you talk about the word ether and the
Yeah, I use that because I'm like an old guy. Like I started studying physics in the 60s.
the word
And a lot of the
ether
material still
brings a
had that
lot
word
of,
in it.
what's the word? It's like talking about ghosts. You know, it's like talking certain subjects, you bring them up and they're like taboo. Okay.
Yeah. But I'm old
Ether's
school.
one of those taboo subjects. And
Yeah. What do they call it now? Remy might know.
well,
What do
no,
they call it now?
They call it vacuum energy. Or they call
Okay,
it-
dark energy.
But they also talk about like these virtual electrons and positrons popping
Right.
into existence and all that kind of stuff, which I frankly don't buy that. I think it's of course I have what is it called? I have my own biases.
Well,
Okay,
does
what I
anybody
think
have a
is
copy?
Protons, okay, are in a flux in the universe, and there's regions of low flux density, like where we are, because our sun creates a bubble around it of protons that are coming
Right.
from it. Okay, but the intergalactic space has got higher flux density of protons. Okay, but
Right.
that's intrinsic. It's like an intrinsic value of and that's the energy that we're talking about. Is these
It's interesting.
protons moving are creating an energetic field that we
You have to read. I'll have to read up on it some more. The one paper that interested me was there was one paper that Albert Einstein tried to publish. He sent it for peer review. The guy that was supposed to peer review it sent it to a couple other guys without asking him, and they had him pull the paper. Right, it's the only paper that they ever pulled of his. Never got published, and they had a problem with the title right off the bat, which was "Gravity Does Not Exist." Right. And I'm trying to read the thing. I found a copy of it online in German, but it's like a photograph of it. And I was trying to find a text version of it because I'd love to see what it was that he never was able to publish about the subject of gravity and how it works. Right. But I read all of his other papers, and he's always very careful to talk about gravity in a certain way. And even his colleagues were back in the day about what it is and how does it work. But I'm really curious to see what that paper is that they rejected of his. I don't know if anybody knows where I can get a copy in English. That's the title of it.
I heard a lot of his work came from his wife.
Maybe that's behind every man there's a woman, right?
I heard that the rumor I heard is that he wasn't so good at math.
No, he wasn't.
And his wife was great at math.
And he was the front man?
And in reality, even though he won the Nobel Prize, his wife got all the proceeds. Now,
That's
I think
interesting.
there's a reason for that. Besides,
Wouldn't shock me. Wouldn't shock me at all. But I'd love to get a hold of that paper.
oh, that
and
was
read
his
it in English.
ex-wife at that point, by the way.
Well,
Okay.
I was going to say the wife always gets all the proceeds. That says nothing.
In the divorce, yeah.
So, well, so Michael, let me see if anybody else has questions here. Who else has questions for Steve?
I have a question.
Yeah, go for it, Harold.
Okay, what I want to ask, very interesting conversations, a lot of futuristic stuff, look like a lot of promising research. So I ask you, give me, what do you see coming down the pipeline in terms of gravity research, anti-gravity metamaterial that will help a spaceship better, especially for the military in the near future? What do you see there? Give me your educated guess.
Okay, my guess is a low budget version of it, which I think they might already have. I should elaborate a little bit on this, right? I'm pretty sure they have what we're talking about, and I'll tell you why I think that. I used to live in Arizona, in a town called Maricopa, right? It's just south of Phoenix, near Casa Grande, if you know the area. Huh?
That's all over the news now. with all that was happening there.
Oh, okay. I didn't know. But I lived there. I had a house, and there's a highway that goes from Phoenix out there, right? It's really long, dark at night. Some parts are lit, some parts aren't. I drove up and down that. That was the only way to get to Phoenix. There's one road, right? And if there was a traffic accident, you're there for hours. But anyway, on this road, I noticed I was driving with a friend, and he's in the construction business. And there was this, it's all Indian reservation, wild horses and whatever. There's nothing out there, absolutely nothing. And all of a sudden, there's this one ranch house on reservation land with a long driveway off the road, and not much. It looked pretty whatever. And he said, well, yeah, he pointed that ranch house to me. And I said, yeah, I've seen it a million times. It's probably, owned by the tribal people. He says, I don't think so. He says, number one, look at it. And I said, yeah, it looks like maybe a 2-bedroom ranch, maybe that. He says, how many cars and vans are outside of it? And I said, wow, there's like a dozen. He says, where are all the people? They're not out on the ranch. So they must be in the house. And if they're in the house, they're standing shoulder to shoulder. There's nowhere to move. I said, okay, I'm a little, okay, fine. But then he pointed up to the power for it. So the power lines are up there. You have main power lines to run out to Maricopa and beyond. And he's like, you see that transformer up on the pole there? I said, yeah. He says, that's not for a house, Steve. That's for a factory. They're running enough power to that house to power a factory. So I said, okay. So I called up a buddy on the East Coast that works in defense, and I said, if you guys have an operation going there, the locals are getting suspicious, right? So I think it was like a month later, they put this sign, they built a little sign thing at the front. It was like one of those brick things, and they put a sign on it that said, U.S. Space Command. So apparently my buddy was right. It's some sort of underground thing. And they put this thing on U.S. Space Command. And then, so that was there for a while. Then they took the emblem off and they put another one on it. It said something else, U.S. Air Force something or other. Then they took that one off and put something else. And finally, they just took it off, and there's this placard there sitting there. But here's the interesting part of the story. So I was driving on that same road with a couple, a married couple, and we happened to be discussing these topics about UFOs, UAPs, and so forth. And lo and behold, right over where that location was this triangular craft. It was massive, massive. It was lit on the edges. It was sitting there. We pulled over. Thing was dead silent. I'm going to say 2,000 feet up, directly above that, whatever you want to call it, Space Command thing. And we're watching it. They wanted to take pictures, and I discouraged them, because I figured it was one of our craft, And then the thing just took off so fast, you couldn't follow it with your eye. It was gone, right? And silent too. There was no noise. So I'm pretty sure they have something cooking there, right? In other words, the things we're talking about, the military probably has a lot of this stuff. I think they have a low budget version as well, which is like where they took like some A-10 Warthogs and maybe some other aircraft. And rather than spending all the money to make them, you take an existing aircraft, right? And you put in some sort of a lifter, if you want to call it that, or some sort of, part of the system that just gives it lift, nothing else, not propulsion, nothing else, right? And so budget-wise, you've just got that. And you have this craft. And again, Linda Moulton Howe, somebody sent in photographs of these things, and I looked at them very carefully. And they were reporting that they had sounds of jet engines like right over their house, really loud, and then they would cut out, right? And then they would start up again and cut out. They couldn't see anything. They're looking up in the sky and so forth. And imagine a low budget version where you get an aircraft like a Warthog. It's got the lifter, so you take off. You could do a short takeoff and landing situation, right? But you're using your regular jet engines, okay? And you just fire the engines up for a while and then coast. And you could use the regular, ailerons and everything to go. You can even go up to the jet stream and ride that for a while, all without burning fuel, and silently too, if you're not running the jets. And if you turn the jets off, once they cool off, you won't have a thermal signature. So that's pretty good, right? And then finally, these craft, they said they were invisible. And I saw the photo. Somebody took a photo of them when they were, what do you call it, decloaked. And they were all white. Every part of the plane was white. And I could see they had four A-10, Warthog aircraft, and then they had a refueling tanker with it, which I recognize as KC, I don't remember what the designation was. And then that thing had this weird popsicle stick, I call it, on the back, on the tail. So it was strange. They were all white. And I thought maybe they put a coating on it where they could energize it and it would have, you know, it'd be invisible, negative index of refraction type situation. And if you look at that, that's a cheap way to get tactical or strategic advantage without spending a ton of money. You know, you coat your craft with something that makes it invisible to radar and also visual light. You put this little one lifter or whatever they are to get rid of the lift issue. And you use your standard jets and jet fuel to propel it around. But if you think about it from a combat scenario, you could get these things near the theater and get them going at a pretty good speed and then shut off the engines and let them cool off. And you'd essentially be invisible and silent. And then you could attack from the air. So I think they're already doing things like what we're talking about. And for the future, I guess just imagine that they're continually, you know, improving and dropping the cost, you know. But the one thing when I saw that triangular craft, the only thing I could think of was how long were they doing this and how much did it cost? Was it 50 billion? Was it 100 billion? Was it 10 years? Was it 30 years? How much went into it? How many people died? You know, test pilots, scientists, who knows? That's all I could think of was cost, you know.
Look like, you know, that was very perceptive of you to notice that transformer, because look like when they installed it, everybody else missed the clues, what it would give out. And I'm going to ask you the next question, because look like you know a lot, and I want to take it to the edge. Now, about 10 years ago, maybe more than 10 years ago, I saw that the Japanese did, you know, the invisibility cloak. And in the video, it worked so extremely well. It was incredible. Now, I had never heard of anybody, you know, in the Defense Department or any project or anything that they're using that invisibility cloak to be, you know, to make airplanes invisible. They talk about, you know, the Black Project and so on, you know, like the F-114. The invisible, but I never heard of that. I mean, what do you know about that? I mean, have they done any project like that in which they can shroud it with invisibility, with metamaterial, however they do it? But I know the Japanese did a very good job. What can you tell me?
When I left defense, the whole thing, and I worked on some of these projects, was we had low observable, then we had VLO, right? So we had LO, then VLO, which is very low observable. And then we had ELO, which is extremely low observable. And this had to do with coatings and whatever, which are, you know, you can just look this up on the internet now. It's anti-reflective coatings for radar, essentially, right? When I worked in defense, we had these coatings for the military aircraft. And one day, some of the guys took a van and they put this special paint on it. You had to bake it in an oven to cure it. So we put it in the oven or whatever. And then it was that we had it out on the runway and we had a cop that we knew come in with his radar gun. And a van is probably the easiest thing to track on with a radar, right? Because it's flat sided. The hardest thing to track is a VW Beetle with the rounded surfaces, really tough. But this one was easy, right? And he stood on the side of the runway and somebody drove up by him doing about 80 and it didn't even register on his radar gun, right? So those are the types of coatings that we had that when I left. And I knew people that worked on the F-117, you know, and my friend was the director on the B-2 program, but we don't talk about the very specific things, and I still don't talk about those things. But all I can say is that was back in the 80s and early 90s. So I would imagine they've progressed quite a bit. And from what I could see, maybe they have, you know, conquered some of these issues with even the what we'll call invisibility to visible light as well. It wouldn't shock me if that were the case.
I haven't heard anybody, you know, in the defense or program, anything, you know, and I was in the Air Force many years.
Right.
That anybody is thinking of making an airplane optically invisible, because for a fighter pilot, for example, being up in the sky and having an airplane like the invisibility cloak that you don't see it with your eyes or with the radar, I mean, it's quite an advantage, but I haven't seen about it.
Yeah, no, absolutely. And if that stuff is going on, it's going to be in black programs way off to the side. Servicemen are not going to know about it. And the ones that do, that interact with the craft, that deal with it, are going to have these special clearances with lifetime secrecy, right? You know, I've signed a bunch of them. And it's just, that's the way they're going to manage it. And that's the way they should, because they're spending gobs of money on this stuff. And if they do get it, they don't want to just parade it in front of the public, because that also includes our opponents would also see it, right?
That's
So,
true, you know.
right.
Yeah.
Thank you.
Well, thank you, Harold. So let me go to Mark Sokol, and we've got probably just about 15 minutes left, Steve, if you're okay with that. And
Yeah, sure.
okay. Mark, go
Hey.
for it, sir.
Hey, Steve, I'm here in the
Hey, Mark.
Falcon Space Lab. I heard you talking before about inertial mass cancellation, or making something weightless. That's actually something that we're working on with the Alzaphon experiment, which is we're trying to create coherent matter states in the core of the atom, like get all the spins oriented.
Okay.
What was your theory behind what makes matter weightless? Like,
Yeah. First, before I say that, is there some sort of a link where I can read up on your project? Because I did see a spreadsheet where you have tasks and everything, which look like great project management you're doing. But is there somewhere I could read on it and see an overview?
an overview. I mean, there was presentations here at APEC, and we just give updates every time. I'm going to show you guys it live in a couple moments.
Okay.
And you can come down to the lab and help out with it hands-on.
Where are
if
you
want.
located again?
Hawthorne, New Jersey.
Hawthorne, that's right.
Well,
Jot
and
that
Mark,
down.
don't forget, in between then and now, yeah, we do have Ken Griggs, who's going to walk us through Phoenix theory. So
Oh yeah,
Okay.
I'm real excited to hear about that.
Maybe-
But,
Maybe
I
Mark,
just
if
wanted
you
to
could
ask
send me
you.
a link to it and I'll read on it before I make any comments. You know what I mean? I'll like immerse myself in it.
okay,
You know.
it's basic. Sam Thompson's actually holding up the book, Gravity Control with Present Technology. That is the book that his son wrote. Frederick Alzaphon's son, David, wrote that book. And there's also
Gravity control with, okay, I'll Google it and I'll buy a copy. Let's say that. That's a probably good place
that's
to
on
start, right?
that's an Amazon. But the real scientific paper is it's available online. It's called Anti-Gravity with Present Technology.
Okay, let me write that one down. Okay,
It's from 1981.
81. I think I've seen that one. I've never read it, but I've seen it around.
Yeah,
With-
that's the experiment I'm working on.
Okay.
Also, are you working on any experiments?
Are you kidding me, man? I'm so busy. I barely had time for this. I'm doing quite a few other different projects completely unrelated to this. Some stuff with geopolitical analysis, some stuff with we're looking at crop projections. So it's for a hedge fund, so they make investment decisions based on analysis, and so that's taking up more than half my time. And
So
the other
where
half,
hedge
is
funds
taken up by-
stand on anti-gravity investments?
What is what?
Where's the hedge funds and the anti-gravity investment?
You know, it's funny. I
investings
had
here?
this chat with Eugene, and I said, Eugene, because he sent me his presentation, you know, his pitch, right? And I said, I know a lot of VC, I know a lot of them, all over the planet, right? The big ones. And I said, none of them have a flying saucer fund, right? Because you go to a VC or whatever, they have, you know, they have your alternative energy guys, and then you have your physics, and then you have your, you know, they have everything. Social media is a big thing, whatever. And I said, none of them have and I said, this is usually governments do this type of thing, not private investors. I mean, it's a big ask, right? So I was like, if you can come up with something for alternative energy, yeah, right away, walk in, and these guys are throwing money down on it, you know? So that was my thing to him. But yeah, I mean, the most money I've seen thrown around toward this type of thing is from angels, individual investors that are just really you know, fascinated by the field, and they want to throw down on it, and then they'll give you money. But I haven't seen venture capital, you know, the big players that are willing to take the risk and then tell their limited partners why I just blew $20 million on, you know, anti-gravity. You know what I mean? Like they're always looking for an exit. Where's their exit? Right? You know, so
Oh yeah, I mean, if you're investing in anti-gravity, your exit's going to be
30
a
years.
decade or two
Decade.
out at least. You're talking about starting a company that's going to need to be the size of Toyota in order to be profitable.
Right, or bigger, right?
Yeah.
And have the cooperation of various governments and FAA and God knows who else is going to sign off on the thing. It's a long road, but it's worth pursuing, in my opinion.
And
In my
it has the capability of changing the world.
Absolutely, game
Well,
changer.
So
Yeah.
let me jump in real quick. Mark Steele had a question too. So Mark Sokol, were you just about there or?
I'm done. Yeah.
Okay. I
Yeah,
wasn't
Mark,
sure.
just to follow up with you, what I want to do is read about your project, and then I'll answer your question about how I think my thoughts integrate with what you're doing. Is it fair
Okay.
enough? Okay.
Yeah, I think Remy just posted a link to the paper in the chat, so you can check that out.
Awesome.
Fantastic.
Yeah. And then let me see, Mark, let me ask you to unmute Mark Steele. Okay.
Sure. So I put in the chat, but I'll try to summarize it. I was curious, Steve mentioned the levels of secrecy and everything, and I was a military officer, so I'm familiar with the clearances and stuff like that in the structure. How do you think those apply to like the Pays? I'm not sure if I'm saying his name right, Salvatore Pays patents via the Navy that they filed, because those all seem like pretty far out, almost science fiction-y kinds of things. I've got a good friend who's got 2 graduate engineering degrees from MIT and is a patent attorney for the DOE, including Los Alamos and Oak Ridge and all those types of labs. And she's pretty convinced that the Navy would not file patents like that unless they had something either working or pretty close to working, that they wouldn't be willing to go public, because she said basically filing a patent is the opposite of all those levels of secrecy.
Correct. Right. How they work it, how they've always worked it. And again, I'm speaking up to early 1990s experience, is that the US Patent Office, when they get patents in, if there's something and the UK does the same thing, right? They call it something else over there. If there's something that has implications for national security, before they, while they're processing it, and it takes a while to process patents, provisionals or formal filings, while they get the submission, they run it by the defense guys. And they have tons of scientists, really good ones. And if it looks like it's something that might be, they don't want the public, to be published, they'll vector it off into a black patent program. Right? It's all patents that are black. And if they let it go public, it could mean one of 3 things. One, that's not something they think would work practically. In other words, you're not warm, so they'll let it out. The second one would be, something that's might partially work, but is far enough off where, like, their competitors, and let's call them in my day the Soviets or Russians or the Chinese or whomever, would maybe spend money on, waste money on, right? It might have some merit to it. And the third possibility is that it actually slipped through the cracks. You know what I mean? The patent examiner was like, it was a Monday and didn't catch it, and it went through and nobody caught it in the system. So that's also, you got to hang that one out there too. If it was one
Not
that's
a fourth option that it was actually intentional. They're putting it out there and it actually works because they
I mean,
she's
more than familiar with all those black patent things, and
right.
I mean, she works with Los Alamos and Oak Ridge and all those places, right? She works for the
Nuclear
DOE,
stuff,
so she seemed to think the patent office, even with those kinds of patents, is pretty adamant that if you can't at least show them that there's some chance this thing works, they're not gonna grant you the patent.
Right.
And
right.
that, so there's at least something out there that, I dismissed these patents initially. I read them, and I'm like, this is a BS, or it's just a psyop, or it's just something thrown out there to muddy the waters or something. And I was surprised because she took a completely opposite view of that.
Well, there's another concept that we used to use a lot in the black world, which was HIPS, right? Hide in plain sight. So one is like, yeah, that's it. We're going to put it out there and nobody makes a fuss about it. It's sitting right in plain sight. And their opponents will look at it and say, oh, they would never let this out. This is nonsense.
Right, like your Space Force base that you mentioned. I don't remember where you said it was from, but.
Yeah, it's Maricopa. Maricopa. Yeah. I can show you the exact location, but it's still there. I looked at, from Google Earth, and it was like all kinds of weird stuff happening on that property. Weird things that, and they cut every couple of years they come out with a local news article about what's going on there that never matches up with what I see from the sky. So it's pretty funny. But almost certainly it's an underground base of some sort. The official explanation now, since all this happened, is that they use it to monitor space activity or something. It's part of that network. And that may be true. I don't know. But I saw some other real funky things going on there at one time,
Makes
So-
sense. I'm actually, I find all this pretty fascinating, but I'm an engineer, but I haven't been this deep into the physics for a long time. And so a lot of this is over my head, but it's a pretty
Right.
fascinating
too.
discussions,
A lot of
so.
this is over my head. I just relate what I see and know and my thoughts, and that's about it for what they're worth.
Yeah.
Thank you,
Well,
Steve.
And thank you as well, Mark. Okay, so let me see. I'm gonna mute Mark out. So let me see. Do we have a couple more questions? We have just about 5 minutes left with Steve. Steve, thank you so much for joining us today. That was absolutely remarkable. Yeah, and especially for the Q&A too. You've just really drilled through this. Let me see. Eric Hermanson had asked about, he was talking about inertial shielding. Eric, did you want to try to squeeze in a few thoughts?
Hi, Tim. No, I kind of just blurting out some messages in chat. Inertial shielding. So there's a guy named Paul Marmé, and probably nobody's read his papers because they're in his estate, and you have to go to his estate website to see them. And he theorized that the inertia is from the inductance of a magnetic field while the charged particle is accelerating. And if you read Jackson, Electromagnetics book, 3rd edition, chapter 11, and you look at the radiation reaction force, which is a known phenomenon. If you could somehow shield the back reaction so that you're taking advantage of the runaway acceleration without without the back reaction, the feedback that comes from the back reaction, then you could essentially have an exponential runaway acceleration where you may not feel any inertial effects. I don't know how to, I think that that propellantless propulsion and anti-gravity are things that are simpler than people think. And I think there's many more than one mechanism that works. In terms of inertial shielding, I think that's a tougher problem to solve. And I'm not sure it can be done, but it's hard enough. People talk about 5 dimensions, 11 dimensions. I think it's hard enough to work in 3 dimensions. And I think it's hard enough to get propellantless propulsion to work. So I say let's tone it down a notch and let's just get something to work. Then we can think about all this other stuff. Anyway.
I agree with you. What you just said about there's more than one way to skin this cat. I totally think that's the case. I also think that although I was very interested in that inertia thing and how Poher was saying, that the step one, the baby step, is to get the propulsion thing working, right? I just thought ahead to that one because I'm not working on the propulsion side anymore. How would I tackle that? So I came up with this sort of mental ideas about it. But I did think that if you could achieve that level of sophistication, you might solve more than one problem, more than just the inertial canceling. It might be you're solving a couple of problems at once. I don't know.
I think it's possible to create, it probably is possible to create force fields that are impenetrable, that aren't based on a black hole or white hole creation. I know Jack Sarfati has this pretty cool idea where you can create a white hole where things can get out, but nothing can get in. I'm not so sure you need to do that. I think there's other ways to do that. So you might be able to create a force field shield. If you really look hard on the internet, you'll find some examples of things that have occurred in manufacturing plants where, and one of them was written up in a electrostatics journal where, it seemed to the scientists working in the plant that there was some kind of a force field being produced through the motion of electrostatic charges. So, I think a lot of things are possible. It's just a matter of figuring them out and testing them and making sure the government doesn't classify everything so that we could at least, because that would be a great asteroid shield, right? If we get that to work. So, Who knows?
I
See what
think
happens.
to answer your question, actually, the gentleman before was asking what I see in the future. I think looking at this field now, and I've only been looking at it for the last, I don't know, 6 years or whatever. I didn't even know it was a field before that. But looking at all the data and knowing the military as I do, and knowing the black world, I think they're getting pretty close to like letting chunks of this out to the public to use for the common good, right? The always thing about that, you know, the pushback on that is always non-proliferation, right?
Yes.
Same with the nuclear stuff. It's like their obsession, which is their right to be obsessed. It's a lot of lunatics in the world.
There are, and there's two problems that I see. If it's possible to easily create antimatter or have some kind of nuclear reaction where you get protons or positrons flying out, that's very dangerous, right? You could blow up a city block with a teaspoonful of antimatter, I think. I don't know. I've never calculated it. Then the other thing is,
you can blow up more than that. With that antimatter, it's absolutely, you know, incredible if you get enough of it. Yeah.
Yeah, we can't let that kind of thing out. And then there's the kinetic energy weapons, right? So anything that's over a Mach 5 weapon, it's hard to stop that. And so, I mean, a vehicle. So if you have a Mach 5 or higher vehicle, you could deliver like a nuclear weapon. But that's actually bad, especially if it's a thermonuclear weapon. But it may not be as bad as being able to attain like a Mach 30 and smashing a much smaller heavy object, right?
Yeah, kinetic.
You know, one half mv squared. So the v is to the square, and you could destroy a city block maybe with a softball going at Mach 30. I don't know. I haven't calculated, but you get what I'm saying, right?
I do.
So that's the problem, is the kinetic energy. You know, we don't really want people to be able to launch things that can fly extremely fast, even if they take a long time to accelerate. You don't want that. And you don't want, at least you don't want that till there's peace in the world. And you also don't want, and that's why I created the Peace to Final Frontier peace initiative on Facebook. But you also don't want people to be able to deorbit satellites, or especially like the space station, right? Because that thing's going at what, 22,000 miles an hour, and it's damn heavy and big. And if it survives reentry, that could, you know, that could tear down a row of skyscrapers pretty easily, right?
Oh yeah, kinetic weapons from space are a real problem.
Big problems.
Yeah.
So those are the things you got to classify. But like, we don't really need to have airplane crashes anymore. Why have families suffer, when their loved ones die in an airplane crash, when maybe there's a better way to do it? And
I gave this a lot of thought, looking at this whole thing and seeing, for example, just the electromagnetic, or gravitation stuff that I was working on. Think about it. Do I have time for a quick story?
Well, no, actually, we're out of time, because I'm a minute over
later.
Yeah. So let me do this. Yeah. If you'll be here for the Q&A session later, and if not, we could do it another time. But so let me go back to gallery view real quick, and let me see, mute everybody out. So everyone, please, again, put your hands together and give Steve Lutz an enormous thank you for his time and very long, detailed Q&A session. And again, thank you again, Steve. We're just squeezing up on our time.